Welcome back to the series on short videos of Python functions. Today we're looking at the quad function for integration. The quad function is useful if you can define a function in Python, for example, f of x equals x squared, f of x equals e to the negative x. It takes in something and it returns a value, and you want to take the integral over that function over some domain. The beautiful thing is that you don't need to know the antiderivative of that function. This is a numerical technique for solving for definite integrals. Anyways, let's get to it. So all the functions that we'll use today, we're going to import NumPy, which of course is the main library of Python, basically, matplotlib for a little bit of plotting. The actual function itself, we'll import a library to do a little bit of timing. We'll play around with a few different variants of using quad, how to speed it up, for example. And then this is the plotting style I'm going to use to give a dark background on the plots to match the notebook here. So let's set up a little bit of background so we know exactly what the quad function is for. Well, you know you can define functions in Python. Here's a function f of x, and it's e to the negative x squared times sine x squared. So this is just a function that takes in a number x and it returns a value. And of course, with this function, I can plot things, right? This is just a function. And so I can give a domain. Here I'm going x, 100 values between -3 and 3. If I look at x, it just goes from -3 to 3. And I can plug in each one of these values by feeding this array to this function. It will return a range, another array with all the corresponding values. So then I say y is equal to f of x to get those values. So I have an array x, and I plug in each of these values. This computes the function for each of those values, and I have y. And I can plot it, and I sort of get something that looks like this. So the question is as follows. I've defined a function f of x that looks like this. So I know explicitly what the form of the function looks like. So this is the quad function. It's when you know the explicit functional form of f of x. You give it a number, and it returns something, and you can express this as a function in Python, and it's continuous in x. Then you can define an integral. And so, by the way, a and b can be finite numbers or infinite numbers, but they can only be numbers, right? The quad function is not used to find the antiderivative. It's used to find the definite integral, right? So you don't need the antiderivative to solve this if you use like a approximation method, which is essentially what the quad function is. So the basic usage is as follows. You say quad, which is like taking the integral. I want to take the integral of f, and I want to integrate it from -2 to 2. I want the area under this curve here. Well, it's a very simple function to use. So I get my result, and I get something that looks like this. And you have to think, how do I interpret this? Well, it tells me that this is the answer to my integral. It returns a tuple. So if I want just the actual value itself, I just get result 0, since this is 2 elements. And this value here returns an estimate of the error. So it says I'm returning this value here, and I approximate that I'm about this close to the true value, right? Like you could, because it's an iterative method, I believe that quad uses, it gets closer and closer to the true value, but it's not going to use too much time. And when you're this close to the true value, it doesn't really matter. You can also use infinite bounds, like I said. So here it's going to take the integral from -infinity to infinity of this function. And of course, instead of -2 to 2, it should be a little bit larger because I have these tails here. And sure enough, it's a little bit larger. This is the area under the curve. Now, these functions, f, can take in arguments as well. They can take in additional parameters. So here I have a function of x, but also these a and b, which are like knobs that you can adjust. So it's e to the negative ax squared times sine of bx squared. So these are just like little things. This might be like the number 2, the number 3. There's just an additional parameter that you give. So here with quad, I would say, all right, I want to integrate this function from -infinity to infinity. But I'm going to plug in a is equal to 2 and b is equal to 3. And it's important the way that you order things here. So the way that quad works is it's always going to assume that the first variable is the thing that you integrate over. So x, it's assuming x, I'm integrating over x because it comes in first here. And then there's 2 other arguments, additional arguments, and quad is for one-dimensional integrals. So all the arguments that I feed in here are going to be all the additional arguments here. So 2 will automatically map to a because it's after the first element here, and b will map to 3 because that's after the second element. And so I can integrate like this. I pass in particular values for a and b, and I get a slightly different result because it's going to be a slightly different function than the one above. Now the error that quad returns by default, which is like 10 to the -9 compared to this, you might not need errors that small. And you might think, well, it ran so fast. Why would I want an error any larger than that if I could do so well? Well, often in the case, if you're in a course, in your research or something like that, it takes time. You're doing lots and lots and lots of integrals. And if you can cut the time in half, for example, if you don't need an error this small, like maybe 10 to the negative 5 is fine, then you can take all those integrals a lot faster. So here's a little experiment where I take a lot of integrals. I take 10,000 integrals. And the way I do that is I call quad in here. This is the function I'm calling. And I use this sort of list comprehension so that it gets called 10,000 times. It basically returns a list, but all this is doing is it's calling this function for I in range 10,000. So it does it 10,000 times. And I use this time module from Python. I import this. So this gives me the time before it starts. This gives me the time after it starts. And then I print the change in time in seconds. So I just ran it. And as you can see, it will take, I believe, about 7 seconds, 8.7 seconds. And this is with no changing the tolerance on the error. So it's going to be about 10 to the negative 9 each time, order of magnitude. But of course, that's really small compared to this value. You're talking like the decimal point here or here, which isn't really required. Now here, I'm going to give it less error tolerance. I'm going to say, well, instead of 10 to the negative 9, let's set it to 10 to the negative 4, which of course, you know, is like this decimal place here. So it's certainly not as good, but it will cut the time by quite a bit. So I do the same thing. This is all the same code as above, only I change the error tolerance from 10 to the negative 9, which is the default, to 10 to the negative 4. I do this 10,000 times, and as you'll see, the time goes down to 5.4269 seconds. And you might think, well, 8.7 versus 5 seconds, it's like not a big difference. What's the big deal? Well, when you're taking 2 and 3 and n-dimensional integrals, and you have to wait, you know, half an hour versus an hour, that can be quite substantial when you're coding. So there is a few caveats with using the quad function. And the basic usage doesn't really work with a few functions. And there's many cases like this, and you sort of have to explore them on your own. But I'm going to go over one main one where quad just fails. It will fail to do the integral, but there's a way to get around it. And so here's a function. It's the sum of two Gaussian functions. It's a peak at x equals 700 and a peak at x equals negative 700. And so I can plot this, and it sort of looks like this. If I were to create a limit from like negative 720 to negative 680, you could see one of the peaks sort of like this, and then the same thing from 680 to 720. You can see another one of the peaks, and in fact, if I give it more values here like this, the peaks are a little bit more defined like that. So there's two peaks, but they're spaced very far apart. And I want to take the integral of this whole function from negative infinity to infinity. And of course, these are Gaussian functions with sigma equal to 1. And so, you know, they have a finite width. Like there's a well-known result of what this is equal to. So it should just be twice that, right? Well, let's plot the full function again. Remember, it looks like this. I have a peak here and a peak here, and I'm going to call quad from negative infinity to infinity, and it should return the right result. But it actually returns 0 and 0. So it's actually missing these peaks. The way that quad works is it separates the domain into a bunch of regions, and what it's doing is it's actually missing these. It only works for functions that are kind of, you know, large throughout the range of integration. But for sparse function like this, there's a way to help the quad function. And if you tell it the locations of where these things are non-zero, then it can actually solve the integral. And so that's what I do here. So here, by the way, you can no longer use infinite bounds of integration when you do this. So I know that these are at like negative 700 and 700. So I'll integrate from negative 800 to 800. That should be enough. And I'm going to give it this points argument. And the point says, well, pay special attention to negative 700 and 700 because they're sort of in this domain here. These are essentially like discontinuity points. I know they have a finite width and everything to them, but relative to the range that you're considering here, these are basically like blips. They're like discontinuities. So I say at negative 700 and 700, pay attention to these discontinuities. And I can integrate it again, and I do get the correct value. And it turns out that the area under each one of these curves is root pi, so I can validate this result. And so I have 2 times np dot square root of pi, and I get this value here. And you can see that it is indeed close to this value up into about 10 to the negative 10, which is where the error says that it starts to differ. So you can see that we've helped quad along. Now, this is just a basic usage of the quad function. If you want to know more about this function, of course, in a Jupyter Notebook setting like this, you go quad question mark, enter the cell, and it tells you everything about this function. I hope this was a useful video for an introduction to the quad function for integrating things in Python. If you enjoyed, please be sure to like and subscribe, join the Discord server, and I'll see you next time.